Okay, you still thinking it through, which is natural, okay? Give you a little more time, I think you'd take a good shot at it. First of all, write out what it is VA minus VB. Now, how do you do VA minus VB? You put your two velocity vectors like this. Because you're doing arithmetic on these two vectors, you can start with the vectors at a common point. Okay? Now, VA minus VB is what you would add to VB to get VA. Okay, so what you think of is that very simple equation, right? And now what can you add to one of the vectors to get, to which vector would you add this to get the other? Okay? And you come up with a very simple equation. So this says if you do VB and add VA minus VB, you get VA. So let's say that this is going to be the green vector. Green vector added to VB has to be VA. So now we have VB added to VB, VA minus VB, this plus this equals this. Now if you have the components of these two vectors, then you can express them as i's and j's or ordered pairs or whatever, right? And just do the arithmetic. It's real easy to add them once you know their components, okay? And I haven't given you the information to get the component of this one and the component of this one. And most of the applications you're going to see, they're going to be moving at right angles. It's going to be a little simpler than this picture, but this is how you reason it out. It doesn't matter what the directions of the vectors are, you can represent the picture, okay? And once you've got the picture, if you can figure out the components of VA and VB, which you will be able to easily, okay? So that's a little less easy, and we're not going to worry about that. It's not that hard, so we're not going to worry about it now. You'll be able to calculate VA and VB and just do the arithmetic, okay? And you're going to get this vector. Very simple. So what does this mean? This is the velocity of A with respect to B. So we're looking at it from the perspective of B, and we're looking at how A is moving. Okay? Now, ignore the fact that if you're over here and this is over here, then the way this looks with respect to this isn't going to look exactly like this. Okay, but that would be the relative velocity anyway. County Fair just closed down. You have things moving relative to others. Okay, you think of these vectors. One application I like is, okay, it's like this, and this thing's emitting a sound at a certain frequency. What does it sound like over here? You got the Doppler shift. Hopefully you've encountered Doppler shift, but if not, we'll get to that in a minute. But just like a train whistle, train's approaching, train goes away, the sound goes down. Okay, what's going to happen to the sound that this one produces is this one here. Okay, or that this one produces is this one here, whichever one that is. I'll let you think about that. These vectors will tell you. The magnitude of this vector will tell you something. And actually, you need the components, but
We're not gonna worry about it.
This is a complicated situation. Again, you're gonna see simple situations, but the picture's still the same. If these are at right angles, well, you still have VB minus VA. This happen to be a right angle, as it will for the first problems you see in 2 dimensions. Well, triangle's a little simple, no big deal. Okay. So, if these guys were, if this path overlapped this path, so that they were about to meet, then the guy at B would see this guy approaching him along this direction. Okay, if you superimpose these. So that this point and this point are the same. Oh, that's a bad tangent line. How does this guy see this guy? He sees him moving toward him, right? Okay? Approaching from like the direction out here somewhere. Okay? Or maybe like this. So you want to sort that out. You want to think about it. The equation, though, all comes back to this, which can all be understood in 1 dimension, and it's the same equation. Whether the vectors are in 2 dimensions or 3 dimensions, it's the same equation. And that's relative velocity, very important idea.